Hello everyone. In the previous video, we introduce the silicon germanium phase diagram. We go through some basic information you can get from the phase diagram. And in this video, we're going to talk about a method to compute the fraction of the phases. Okay, so what does a fraction of phases mean? We know that, okay, if we still look at this example where we have this 30 weight percent of silicon and germanium, right? So we know that this is an alloy, and then if we choose a temperature, for example, 1200 degrees Celsius, we know that alloy is in a two-phase coexistence state, right? If we look at the microstructure of what the system looks like, we're going to see that the system is going to compose of the alpha solid phase, right, mixed together with the liquid phase. So that is what we mean by the two-phase coexistence. Now we know that both the alpha phase and liquid phase are solutions, right? So we can use the so-called tie-line construction to find the composition of each of these phases. So this is the atomic structure of the alpha phase. We know is made of a mixture of silicon and germanium atoms, right? But the atoms sit on the perfect lattice because it's a solid. And the liquid, right, the liquid is also made of a mixture of silicon and germanium atoms, but is a disordered arrangement because liquid is a liquid solution, right? But because both of these are solutions, so we can talk about their compositions. And we know that the composition of these two solution phases can be obtained by a tie-line construction. In particular, a tie-line construction is one that you start with a given temperature. For example, this 1200 degrees Celsius. You draw a vertical line across the phase diagram, and that vertical line have an intersection with the liquidus. And then this intersection gives you the composition of the liquid phase, which is 16%. And then the intersection of the tie line with the solidus gives you the equilibrium composition of the solid, which is roughly 64%, right? So, and then the alpha phase is going to have 46% as the composition, and the liquid phase is going to have 16% as the composition, right? This is what we know. Now, because, for example, in this region, the system is made of a mixture of liquid alpha phase, so it's very natural to ask a question, what is the fraction of the alpha phase? And what is the fraction of the liquid phase? Right? So this fraction in this particular case is the mass fraction. For example, out of 100 grams of the total alloy, how many grams of liquid you have and how many grams of solid you have? How do we get that information? Okay, we know that we can compute the fraction of the phases using the so-called level rule. Okay, so what is level rule? Okay, let's spend some time to talk about what happens in the system. Now, what we're interested in is really the mass of the alpha phase and the mass of the liquid phase, right? But we know that it doesn't really matter whether the system separates into different phases or originally is a pure liquid phase, right? So the total mass of the system is conserved. So this is after the system become two phases, but we know that this equals to, like the total mass of the system, before the separation. Originally the system is in a single liquid solution, so is just a single homogeneous phase, right? Now it's separated into different phases, but the total mass still equals to the original one. So we have one conservation equation for the total mass. Okay. Now there's another important conservation equation is the fraction, the total amount of, for example, silicon atoms, right? Now, when the system separates into two different phases, the silicon atoms redistribute themselves into liquid phase and solid phase, etc., but the total amount of silicon and the total amount of germanium, of course, are conserved. We're not losing any silicon, we're not adding any silicon. So now what is the total amount of silicon before the system separates into different phases? Well, originally we know the system is purely liquid, right? And the composition is 30%. I'm going to use this omega naught to denote the original composition of my system. This is before the phase separation. Now, after phase separation, how do we get the total amount of silicon? Well, we know that after phase separation, the system have two different phases, right? So now the silicon contained in the alpha phase simply equals to the composition of the silicon of alpha phase times the mass of the alpha phase. So this is the total silicon in the alpha phase, right? silicon in alpha. And then we have the composition of the liquid phase times the mass of the liquid phase. So this is the total silicon in the liquid. Because the silicon is also conserved, right? So before and after the separation, we know that these two, the total amount of silicon equals to each other. So if we consider both of these two together, in particular, we replace the total mass using the mass of the two phases. This allows us to write down this. And then multiply omega naught, right? And then we can rearrange the terms a little bit, right? So we can basically arrange all the terms associated with the mass of the alpha phase on one side. So this is going to be mass of the alpha phase, and then we can arrange the mass of the liquid phase on the other hand. This is the mass of the liquid phase. So this allows us to write down this very interesting relation, which is the ratio between the mass of the alpha phase and the mass of the liquid phase is given by this. Okay, so this is what we call the level rule. Okay, what does this mean is the following, right? So as you can see here, we have three important compositions. This is my omega naught, right? And this is omega L, this is omega alpha. So now what is omega naught minus omega L? What is this? Omega naught minus omega L is the length of this part, right? Basically this part. Now we call this the liquid arm because it's basically your original composition minus the liquid composition. We call this the liquid arm. And then omega alpha minus omega naught is particularly this length, right? We call this the solid arm, okay? Now what you see here is that the mass, the ratio between the mass, which is also the ratio between the fraction, right, of the solid phase and liquid phase is equals to the ratio between the liquid arm and the solid arm, right? So it's pretty much like you construct a lever, right? And they have these two arms and you're balancing these two things. So that's why we call this a level rule. And you can easily write down the fraction, right? In this case is the mass of the alpha phase and then over the total mass. And that equals to this. Okay, and then the mass of the liquid phase again is the liquid over the total mass, which equals to, this is a solid arm over the total length, right? So this total length is the composition of the alpha minus the composition of the liquid, which is this length. Okay, so this is what we call the level rule. Okay, now how can we use that? Well, because we already identify all the compositions we have, right? So again, what we're interested in is the fraction of these two different phases, right? And now we know, okay, these fractions are related to or can be computed from their compositions. So what we have to do is just to list their compositions, right? There's three compositions we have to work with. The first one is the overall composition of the system, which is 30%. And then the alpha composition is 46%, and then liquid composition is 16%, right? So these are the three compositions we have. And then we can use them immediately and use the level rule to get the fraction of the alpha phase, which is, again, this is the overall composition, 30%, minus liquid composition, 16%, and then you have, this is the alpha composition, minus the liquid composition, right? So you have 14 over 30, right? So that is basically going to give you less than, a little bit less than, I would say 50%. This is roughly speaking, right? 48%. And the liquid fraction of the liquid simply equals to, this is going to be, again, the alpha composition, 46% minus 30, and then this is 46 minus 16, and you have 16 over 30. I'll say roughly this is 52%, right? So this means that if you have 100 gram of your total system, 48 gram of that system gonna be alpha phase, and then 52 gram of that gonna be the liquid phase. So now we can go back here and label. Okay, this is going to be 48%, and this is going to be 52%. Okay, so that is level rule. Okay, level rule allows us to compute the fraction of each faces based on their equilibrium compositions. Okay, and then the way how we get a level rule is by this conservation equations, because the total mass is conserved before and after the phase separation, and then the total particular type of atom is also conserved after and before the phase separation. So we can use those two conservation equations to derive the level rule, which allows us to compute the fractions of each of the phases.